Fellow in Quantum Software and Information at the University of Technology here in Sydney. And Peter is also a mountaineer, musician, cryptoanarchist, and author of the recently released book, The Quantum Internet, which is going to be the subject of our conversation here, pictured right there in Peter's hand. So, Peter, thank you very much for joining me.
Thanks for having me on, Sam.
So I was thinking about diving straight into the quantum side of things, but in doing my research, I uncovered that you got expelled from preschool, a Montessori school.
Yeah, so that was my first academic achievement.
Yeah. I mean, we don't need to get into the story there, but I guess is rebelliousness or thinking
that was the exact word that I was about to use.
Yeah. So has that characterized your, I guess, view of the world or the things you've been interested in to a certain degree?
I would say so. But when you said the word crypto-anarchist before, I think that also suggests quite strongly that there's some rebellious attitude in there. But yes, I do tend to have unorthodox views on a lot of things and promote them regardless of whether they're sort of mainstream or not.
Power to you. We need more of that. So I guess before we just dive into the meat of the conversation, how did you get into how did you get into physics? How did you get into the quantum side of things?
Yeah. So since I was a kid, I was fascinated by really two things. One was engineering and the other one was physics. And at that age, the field of quantum computing didn't exist. It was a non-thing. It was just interest in theoretical physics at a young age. But when I went into undergrad university, I decided to go into engineering because at that time, quantum computing also wasn't much of a thing, at least not very widespread and not very well known. So I went into computer systems engineering, but I took physics subjects as electives just out of interest. And then as I started proceeding through my undergrad, I realized that there were a bunch of researchers in my field at my university, that was University of Queensland in Brisbane. And so I approached them to see whether I could do my honours project there. And at that point, I bifurcated and switched into quantum computing and subsequently did my PhD in that field and have never really gone back.
And quantum computing, your PhD was at UQ?
Yeah, that's right, in purely theoretical aspects of optical quantum computing.
Yeah. Well, shout out to UQ. It's also my old uni, so beautiful place.
Yeah.
So quantum computing, this word quantum has so much baggage. I think every mystic out there, every new age person has just like bungles in quantum to, try to spruce up their marketing and make whatever they're talking about seem more legitimate. But this whole quantum computing phenomenon or the developments there are very much real. And what I think is so cool is we are taking quantum physics, and this word quantum has so much of that that magic or that power because the quantum realm is so bizarre to us. Like it's completely, it is counterintuitive.
It's counterintuitive, and when you learn it, you really have to throw away all your intuition altogether and try and pretend that you're a baby learning from scratch in a whole new, different world.
Yeah, but the cool thing is we can harness it. It's not just like this theoretical. It's not just theoretical. We can actually now with quantum computers, we can actually put devices together that do useful things.
Yeah.
So I guess. What is a quantum computer? How do they work, and how are they different to conventional computers?
Right. So there are different ways to explain it, depending upon the audience, because it is much harder to explain the nuances of quantum computing than it is classical computing, just because classical computing is so easy to conceptualize. Like you don't have to have training in computer science to get the idea of what transistors do and how logical gates work and how they implement elementary algorithmic operations. It comes fairly naturally even without training in the field. But for quantum computing, it's quite different. I mean, we still have notions of circuits, for example, but the way to think about it is very, very different. And the way in which different quantum algorithms get an advantage compared to classical algorithms depends on the algorithm. It's not a one-size-fits-all answer. But one thing that they all have in common is that the quantum computers don't rely on purely digital information, which is normally thought of as zeros and ones. We rely on qubits, which are able to be in superposition states. So you still have a logical 0 and a logical 1 state, but the ability to be in superposition. In other words, in some sort of hand-wavy sense, a mixture in between the two with some, not probability, but simultaneously different elements of both. So it's different to like a classical bit that's probabilistically, 50% 0 or 50% 1. But now it actually is 50% 0 and 50% 1. That's what a superposition is. And then the other feature that quantum computers exploit is quantum entanglement, which is when you have multiple quantum particles or quantum bits that are jointly in superposition. So if you imagine two quantum bits, and this one can be, imagine quantum bits that are made from particles of light, photons. So polarization is a concept that most people will be familiar with from high school. Light can be polarized in different directions. So imagine that we say if a photon, a particle of light, is horizontally polarized, we'll call that 0. And if it's vertically polarized, we'll call that 1. And it can be in a superposition of one or the other, or both at the same time. Now imagine we've got two photons. Imagine instead of each one independently being in a superposition of horizontal and vertical, they're both jointly in a superposition of horizontal and vertical, but such that they're correlated perfectly. So they're jointly in a superposition of both of them being horizontal or both of them being vertical at the same time. That is what entanglement is, and it can extend to any number of particles, but for two particles, that's how you can think of entanglement. And so quantum computers have both superposition and entanglement within them. And essentially they exploit the fact that as the number of qubits grows, the number of possibilities that can be in superposition simultaneously is growing exponentially. So if I give you 10 classical bits, there are 2 to the power of 10 possible combinations of what those 10 binary digits could be. But it can only ever be one of them at a given point in time. If these were quantum bits, you could have a superposition of all 2 to the power of 10 of them simultaneously. Or if you generalize that to n quantum bits, 2 to the power of n, all simultaneously. Now, some people talk about this idea of quantum parallelism, the idea that this means that you can simultaneously process all computations at once. That's not really a correct analogy to make, but it is correct to say that all of the quantum algorithms in one way or another exploit the fact that information is encoded in superposition such that within your device there are multiple states of information in superposition. They're being processed in superposition, and then you do some kind of tricks using interference to get an output that gives you something reflective of the global state of all of those different combinations. It doesn't mean you get all of the answers at once, but you get some sort of something that says something global about all of those different possibilities.
Okay, so I'd like to ask a bit more about the qubits, but right now, how? So I initially I thought that perhaps they do run all these like computations at once in a way. They explore all potential pathways and then spit out an answer. So you're saying that's not the case? Okay, well, cool.
Okay, so sort of. So it is true that if you make put your qubits into a state of all possible inputs in superposition and then put them through a quantum computation, the output will be a superposition of the computation applied to all possible inputs. The problem is that with quantum physics is that when you measure something that's in superposition, you don't get all of the answers at once. You get the measurement collapse problem. So we've heard of this Schrodinger's cat paradox, the idea of this cat being inside this box that both is alive and dead at the same time. But the moment you look at it, you never see the cat being alive and dead at the same time. You see it either being alive or either being dead. So the process of observing something collapses superpositions onto one particular state. So it may be the case that the output to a quantum computer has all of these different answers encoded into it. But when you measure it, you can only get one. So that doesn't give you any advantage. That's exactly what a classical computer does. What you actually have to do then is apply some tricks, which you do using interference, to interfere those different answers with one another, such that you get a single output that says something characteristic about the entire space of inputs. Doesn't mean you get all of the input states.
Okay, so just to make sure I'm understanding, you've got all of these qubits, and they create all of these bits. Like, just imagine lots of lines, and each line represents a single computation, or one of them. Interference causes them to kind of mess around with each other in such a way so that we can maybe select the ones that are more useful, or that give us some sort of answer towards the end.
So here's an example of one of the first quantum algorithms called the Deutsch-Jozsa algorithm, named after the computer scientists David Deutsch and Richard Jozsa. And the idea there is you have a circuit, and it does one of two things. Either for all of the inputs, it gives the answer 1 at the output, a single bit answer 1. Or for exactly half the inputs, it gives you a success. So it detects whether the circuit is what's called uniform or balanced, whether it gives the same output for all inputs, or whether it gives different outputs for half of each of the inputs. It's able to distinguish those two. So it does that by taking all possible inputs in superposition and then doing an interference trick, such that you get constructive or destructive interference in such a way that the single output at the end is able to identify whether that circuit is uniform or balanced for all possible inputs. It doesn't mean it gives you answers for every possible input. It gives you this global sort of answer.
Okay. That makes a lot more sense to me. So what sort of, like, my understanding is quantum computers will not replace classical computers, because there are many things that classical computers just do better or faster, but they do unlock solutions to problems that classical computers struggle with. Is that right?
That's correct. So there is some misrepresentation in the media that quantum computers can speed up everything. Well, that's
the
actually
media's misrepresenting stuff. They're sensationalizing things. Oh wow!
The trouble is that in the field of the quantum space, it's not always intentional. Sometimes it is a bit nefarious, but sometimes it's because it's just really nuanced, and it's easy to just not get certain nuances. Sorry, what was the question again?
Can't blame them. I said that quantum computers are better at solving some problems.
That's right.
But classical computers are better at solving others.
That's right. So there's a select class of problems where quantum computers can give you an enormous performance improvement compared to an equivalently sized classical computer. But for most everyday purposes, that's not the case. Quantum computers do not speed up the sorts of algorithms that we have, like the ones we're using right now in front of us. They don't speed up things like computer games or video game graphics. People often ask that kind of question. This is going to make my ray traced GeForce quantum chip so much better. The answer is no. We don't have any known quantum algorithms that speed up those kinds of things in particular. So some of the things that quantum computers are known to speed up include certain types of optimization problems, certain types of code breaking problems, various fairly abstract, hard to describe mathematical problems, and in particular, one that is of enormous economic utility is quantum simulation, which is simulating other quantum systems. And that's enormously important. So imagine that you're simulating chemical interactions, for example. They're inherently quantum mechanical in nature, the way that molecules and atoms interact with one another. If you try and simulate those on a classical computer, well, we can do that, but we use all sorts of approximations to get rough answers. If you map it across to a quantum computer, you can do it far more efficiently. So that has huge implications for things like materials engineering, potentially drug design, especially as we move into the era of individualized medicine, that it's genetically targeted, where you want to be able to simulate the way a drug might interact with someone's biology without having to perform mass trials, which by definition you can't do if it's individually tailored. So if you can properly simulate it in advance, you can bypass that and speed up that whole pipeline. So those are the sorts of areas where you get enormous improvement. But the typical.
So could I just jump in and ask a question to bring it, just to connect back to all those things going on simultaneously and using interference to try to get to some global results? Would that, let's say that global results in the context of testing drugs for a specific person, you'd input their genetic profile or whatever, and then you're looking for the results. Let's say there are no problems. That's all we want to know, right? Like, is this going to be harmful, or is it going to be?
So for example, what you might want to do is ask the question: if I take these two molecules, how are they going to interact? As in, like, all the different electron distribution, the electron shell distribution around it. How is that going to interact and bond or whatever to create a new molecule? What will the structure of that look like? So the analogy I gave before about finding a global answer about all possible inputs, that was for that particular example. For quantum simulation, it's not quite like that. You are literally doing a one-to-one mapping of a physical system to a quantum computation. But yeah, if you want to answer the question, is this drug molecule that I've just invented going to interact with someone's molecular biology in a certain way such that things bond in a way that will enable the drug to activate this or that receptor or whatever the case may be? Answering questions like that, which is quite hard to do using classical techniques, at least accurately.
Okay. So you said the sorts of problems that they'll help us solve, cryptography or things related to
certain cryptographic applications. So they're the big one, and this is the one where really all the money came from in the early days of the field of research. The moment that Peter Shaw came along with this paper that showed that you could crack public key cryptography, specifically the RSA cryptography that we're using right now to secure this internet connection, he described a quantum algorithm that allows you to efficiently take the public keys, in other words, what you can intercept on a communications channel, and use that to figure out what the private keys are to read the messages. Classical computers would take an astronomical amount of time to do that. Quantum computers can do it much more efficiently. So at that point, all of the military and defense intelligence agencies came in and started pouring money in and saying, oh, we've got to have this. And that's sort of one of the things that really sparked interest in the field early on, at least from an investment point of view.
Yeah, okay. I want to put a pin in the whole security encryption side of things right now, just because I think I do have hope, though, because you say cryptoanarchist, so that means crypto might be safe from the quantum from quantum computers. But yeah, we'll come back to that. I want to just talk about qubits for a bit. What can we use as qubits? Because, like, to me, like if I think of bits, I think of things I think of something on a circuit board, and they can go on or off, right? But what can we use for qubits?
Yeah. So in the same way that classical bits, I mean, usually we think of them as being electrical signals going transistors. But in principle, a classical bit is more abstract than that. An abstract bit is just anything that can be one of two possible states. It could be pen and paper where you draw ticks and crosses. That gives you classical bits. There are two choices for each symbol that you use. So in classical computing, we do that with electrical voltage levels, and then the computations are performed by transistors, but it could be anything else. Quantum bits are quite analogous, except that it has to be a quantum system that we're talking about. So any type of quantum system which is capable of being in a superposition of multiple states at once, or specifically two, you could use those two different quantum levels in that system and map them to calling them 0 and 1. So examples would be, if we're using light, horizontal and vertical polarization of a single photon. We could take a single atom, and if we remember back to chemistry, electrons can have different energy orbitals, right? And it can change between those. If you hit an atom with some radiation, the electron can jump up to a higher energy level. And that's how you can get a transition between logical values. So an atom with the electron energy levels can give you a quantum bit. There are other types of quantum bits using superconductors. So if you take a small superconducting ring and you imagine current can flow around in a loop through that ring, and it's superconducting, sort of effectively just keeps going around forever with no drama. You can actually put the current flow into a superposition of being in the two different directions, clockwise and counterclockwise at the same time. That can also be a quantum bit. And there are a plethora of other possibilities. And researchers are looking at different ways of doing things in parallel. Because we're so early in the stage of developing this technology, we're not even sure what the best way to actually build a large-scale quantum computer is. There are big companies that are investing heavily in trying to do it optically. There are others trying to do it using all of the other conceivable ways of building qubits, and we just don't know the answer yet.
So I just want to talk about light, because I think of, and is that what you mean by optically, like using light as the qubit?
That's right.
Okay, so would the light be, so in my mind, light always has to be moving, right? Like light can't be stationary. So in this, which is kind of funny, I guess, like this never struck me before, but light always has to be doing something.
Yeah, they're traveling qubits.
Yeah, okay, so would they be traveling from point A to point B, like just like bouncing between mirrors, or?
The way that the companies and the labs that are building optical quantum computers work is they fabricate little optical chips using what are called waveguides, so little etched out sort of little regions where the light can propagate through, and it goes through from one side to the other, and as it propagates through, you have all sorts of optical components that makes the light interfere with one another, the different optical modes interfere with one another, and then at the output you get your computation.
Okay. It's incredible. Like there's just the amount of I just taking all this knowledge and then building stuff to take advantage of this natural phenomena is crazy. So there's a lot of, it seems to me there's a bit of a race, and I remember reading articles just over the past few years, a few in Wired, to achieve this thing called quantum supremacy.
Right.
So what is quantum supremacy? And it sounds very important, and it seems to be quite important from what I've read. What is quantum? What is it?
So this is one of those things where it's worth clarifying some of the nuance associated with it. So technically, they use the term quantum supremacy to mean the point at which we have quantum computers that are able to very substantially outperform the best classical computers. The definition of very substantial is kind of arbitrary. They just choose some big number. But
is that as for a set of problems as well? Is that for a set of?
So in principle, that definition could apply to any specific problem. And that's when, so you may recall, if any of your listeners read the popular press when those headlines came out about Google reaching quantum supremacy. Here's the caveat with that. They built a device, a fairly small scale device, but it's able to implement a particular problem far, far more quickly than the best classical computer would be able to do. So it can do in seconds what the biggest supercomputer would take years, that kind of difference. However, it only solves one very specific problem, and it's one that is contrived for the purpose of demonstrating that you can do something with a quantum device that outperforms the best classical device. And it turns out that that problem is not particularly useful for anything at all. It's really proof of principle. And in the meantime, similar things have been done optically. So the Chinese team in Shanghai, they have recently made similar claims using an optical quantum computer, but it's not what we call a universal quantum computer. A universal quantum computer is one that we can program it to do anything we want, at least in terms of what algorithms are capable to do. These ones are solving very, very specific problems. Those problems are chosen on the basis that they're within the realm of what we're technologically capable of doing at the moment. They're not chosen because they're actually doing something useful like code breaking or a cool optimization, whatever the case may be. So all of these demonstrations where they claim quantum supremacy, you need to take that with the caveat that it's not a particularly useful problem that they're solving. It's for proof of principle.
Okay. I don't think this is a good analogy, but I'm thinking they develop it's kind of like developing a program to defeat the Turing test, but that's the only thing it's good for, defeating the Turing test. I mean, obviously anything that could defeat the Turing test would be useful in other ways, but it's just trying to beat the test and nothing else.
It would be sort of like building a big domino network, that when you flick the first one at the output, it solves like the addition of two numbers or something. You can do that kind of thing. But it's not capable of being programmed, to implement an arbitrary Python program. It's that kind of difference.
Yeah. So can you talk to me a bit about just a few more of the potential applications? I know you said like potential drug interactions. Could we potentially simulate, get accurate weather simulations or
weather
things where there's just so many variables?
Weather simulations, I think the answer is probably not, because with weather simulations, really, the mathematical techniques behind weather simulations ultimately boils down to systems of differential equations, fluid dynamics, and aerodynamics. These are things that classical computers can do. The real problem with weather simulation is actually the fact that they're chaotic systems. So we've heard of the butterfly effect, right? A butterfly flaps its wings here, and a year further down the track, that could result in a cyclone on the other side of the world. It's one of these crude analogies, but it's actually completely accurate. In a chaotic system, you have the tiniest change in the initial conditions, and then not long later, the output looks completely different. Billiard balls on a pool table is the same system. So the limiting factor with weather simulation is that it's a chaotic system, and you can only know the current state of the global atmospheric system with a certain level of precision. And it's that level of precision which limits how far ahead you can predict. It doesn't matter how powerful your computers are. Computers are infinitely powerful. If you have a very small amount of misinformation in your starting state, you'll get the wrong answer further down the line. So probably not weather simulation. However, a useful one is optimization problems. So consider, for example, a supply chain network. And you can model this as a graph, not a graph as in like a bar graph, as in the mathematical graph where you have nodes
network.
and like a network with edges and vertices connecting them. So a supply chain can be described sort of like a network like this, where you have dependencies. So you have a factory here. It can only produce an output to something once it gets these inputs from the deliveries from those other two suppliers. And those other two suppliers are competing for the road for delivery suppliers that want to produce in a factory somewhere else. And as you build up the work with all of these conflicting constraints, you get an enormous combinatoric problem where it becomes extremely difficult to figure out what the best way to optimize the supply chain network is. And if you make very minor improvements in a supply chain network, given that the entire world economy can be considered as a supply chain network ultimately, if you can even get a slightly better way of optimizing the way that works, economic advantages or productivity advantages. Trying to optimize supply chain networks is something that we do all the time with classical computers, but we use all sorts of approximation techniques because classical computers can't do it perfectly. Efficiently. Quantum computers actually also can't do it if they can do it much more efficiently than classical computers can.
And what do we mean by efficiently here? Like,
right.
What are we talking about?
Yeah. So computer scientists have a very particular way of defining the term efficiency. A bit more specific than the everyday sort of notion of getting things done more quickly. When computer scientists talk about the term efficiency, what they're talking about is how the execution time or the memory usage, some kind of resource usage, usually time, against the size of the problem that you're trying to solve. So if you have, for example, a problem like adding two numbers that are n digits long, the time it takes to solve that scales linearly with n, okay? Because you just do it element-wise and a carry if needed, but it just scales with the number of bits they're adding together. If you're doing multiplication, it's not linear, it's actually quadratic because you have to take every number from the first number and multiply it with every number from the second number. So if they're both n digits long, that gives you on the order of n squared possible things to do. So the computational complexity of multiplication, that's quadratic. Addition is linear. When you move on to things like matrix multiplication, so grids of numbers, multiplying them together, then it becomes cubic to the sort of n to the power of 3 in the size of the matrices. So computer scientists, that scaling, is it n or n squared or 2 to the power of n? That equation that describes that scaling, that's what computer scientists call efficiency. And we usually use the term efficient to mean that something can be done in a time that is a polynomial, like multiplication, n squared is a polynomial, and matrix multiplication, n cubed is a polynomial. That's usually what's referred to as being efficient. Inefficient would be something like an exponential. If you've got a problem that takes 2 to the power of n units of time to solve, well, clearly n doesn't have to get very big until you can't do it.
Yeah. Okay. Thanks for that. So can you just talk me through, so let's say we want to solve, so that supply chain network thing that you're talking about, is the supply chain, is that an example of the traveling salesman problem?
The traveling salesman problem is an example of an optimization problem. It's sort of a specific case of a supply chain network problem, but they get more. And that's an example of one that takes exponential time on a classical computer. It also actually takes exponential time on a quantum computer, but with a smaller exponent. So you're still getting an advantage, but it's not becoming completely efficient.
Yeah, okay. So using this example of a supply chain optimization problem, could you just talk me through how that would work? And I don't mean in much detail, but how it would work as a computation, a quantum computation. Like, what would the output actually be if we were to run one of these? If we were to simulate this, or put in these inputs, what would the output tell us?
Right. So you might ask the question: if I've got, imagine I've got a traffic network, and each road has a capacity of a certain number of cars on it. And I've got all of these cars in these different starting points, and they all want to get to these destination points. That's an example of a supply chain or traffic optimization problem. Now, if you've just got one car and it's got one destination and there's no competition, that can be done efficiently. We have classical algorithms called shortest path algorithms, and they can do this very easily. And it's exactly what you will get from your phone if you ask it, how do I get from here to here by foot on Google Maps? No problem. However, if you have conflicts where now the shortest path of this guy getting from here to here conflicts with an intersection and has to wait for the other guy, as the number of those different conflicts grows, you have to consider all of the possible combination of who gets to use what when, and then it starts growing exponentially. So you would ask the question, what's the optimal way for all of these cars? In other words, who should wait at which intersection to allow who to pass? So who gets allocated what intersection at which point in time, such that we minimize the total transit time cumulatively over all of the people driving in the network. That would be an example of asking a question about optimizing a supply chain network. And with both classical and quantum computers, that's an exponentially difficult problem, but a less exponentially difficult problem on a quantum computer.
Yeah. Okay, cool. So they've got a lot of potential in some areas, and the power of the potential, or the potential of these computers is proportional to the number of qubits that are working in together, that are the number of qubits you have, right?
Right. So if we're talking about the power of quantum computers, in the best case we can get exponential scaling in compared to classical computing in terms of the improvement that we get in runtime.
Because every qubit you add, it just gets exponentially more powerful.
That's exactly right. That's exactly right. Yeah.
Okay, so I guess now we can get into more of the meat of the conversation, or the the topic of your book.
That was the introduction.
That was the introduction. Yeah, just a bit, a 40-minute introduction into quantum computing, so we can talk about what happens when we, network these bad boys together. So yeah, the internet has completely transformed the lives of many people, because not only can our phones do computations, but we can plug into supercomputers and highly trained artificial intelligence algorithms from Google or whoever else, and then we can get that information sent straight to us, right? So the internet's amazing, and that's just using conventional computing. So what happens when we network quantum computers? I don't even know where to begin, but I guess from the limited amount that I understand is that if you have if you've got two quantum computers, let's say they're both 20 qubits each, if you network them, you actually get a 40 qubit quantum computer.
Right.
Is that?
That's right. Yeah. So that's right. That's roughly. That's
when
correct.
Things start getting a bit crazy.
Right. So let's think back to our conversation about the scaling relationships. If every time we add a new CPU to a classical computer, we're just linearly increasing the total amount of power. The power scales, proportional to the number of CPUs you've got. But we were saying before that with quantum computers, the computational power can grow exponentially with the number of qubits or cores or whatever you want to call them. So what that means is that with classical computers, if I've got two of my desktop computers like this one here sitting next to each other, whether they're networked or not, you get the same computational power out of it. It's just that for certain reasons, it might be more convenient to network them so that, you know, if no one else is using the other one, you can take advantage of the unused cycles while the other person is sleeping. But with quantum computing, it's different because we've got this exponential relationship. So the total number of a qubit will be appearing in the exponent, it'll be added in the exponent rather than being added. So if you have a quantum computer and I have a quantum computer, and we both needed to solve the same type of problem that got some quantum advantage. You could either run it entirely on yours, and I can run mine entirely on mine, and it would take a certain amount of time. Or we can unify them to act as one, which is what quantum communications links are able to do. They can unify remote quantum computers. And then we unify them acting as one. We get something far more powerful than the sum of the parts, and then agree that you get to use it for half the time and I get to use it the other half of the time. We just time share it. But by unifying and time sharing, we're going to get much more than just using our individual components separately.
And the marginal, like for every qubit you add to the network, the returns just keep on going on this crazy exponential graph.
That's right.
Like, so,
I mean, if you've got an exponential relationship there, then you don't have a situation of diminishing returns. You get a situation of escalating returns as you add more and more to it, assuming that the particular algorithm that you're trying to run fully exploits that full number of qubits, which may not be the case. But in the best case scenario, yes.
So this doesn't sound like so it sounds great being able to link these things together, but it doesn't sound like an easy thing to do.
It's not. No, because
have we done it yet?
Well, no, because we don't actually have useful large-scale quantum computers yet. So first of all, if we weren't going to connect classical computers, we use the internet that we've got. If we're going to make remote quantum computers act as one, we can't use the normal internet because it only communicates classical information. We need to communicate qubits rather than bits to be able to make distant quantum computers unify together properly the way we discussed. So how do we do that? Well, people are building quantum communications links for elementary proof of principle kind of demonstrations, but they haven't used it for the purpose of linking quantum computers yet because we don't have the ability to do that. What they're doing at this stage in the life cycle of the technology is ultimately using it for something much, much simpler, which is quantum key distribution. So it has very, very simple technological requirements. All you need to do is just transmit some individual quantum bits from one place to another. One side prepares them, the other side measures them. That's all there is to the protocol. And you can use that to, with perfect security, exchange secret keys between two parties. And that's really the stage we're at with the technology that in building quantum communications links. But they've done it in fairly impressive ways. The Chinese, only a few years ago, put up a satellite into
water.
They put a satellite into space in low Earth orbit that allows you to securely share secret keys over a distance of like 1,500 kilometers between distant parts in China, and have perfect security for communications. They did that as a proof of principle. So it's coming a long way, and they're doing impressive things.
So what sort of information could they communicate across these, from one point to another?
Yeah.
Freedom.
All they're doing actually with...
Oh, man. So sorry about that. I just swallowed some water in the wrong way and it went down terribly.
I do that quite often, and it's really hard to get out. The best thing is not to force it.
Yeah. Well, I think it's okay now. So, yep.
So what these demonstrations, let's take the Chinese quantum satellite as an example. What it does is it actually distributes entangled pairs. They call them Bell pairs or EPR pairs, which are just two qubit particles, both of them single photons, it prepares an entangled state where they're in a joint superposition of both being horizontal or both being vertical, and then over a very long distance, receptor dishes pick them up and measure them. Now, that can be used for quantum key distribution that I mentioned. It hasn't been used for this purpose yet, but it can be.
Just to make, sorry, if they're both one, like, so if they're entangled, if you measure one, you know what the state of the other one is, right? That's
correct. That's correct.
Yeah. Okay.
That's right. So if they're in a superposition of 0 and 1, what that means is that if you measure one, you get a collapse, okay? So you don't see 0 and 1 at the same time. It randomly collapses onto 0 and 1, like the Schrodinger cat in the box. But because they're entangled, if you measure this cat as being alive, the other one is guaranteed to be alive. And if you measure this one dead, the other one is guaranteed to be dead as well. So if you measure one of the photons and it's horizontal, you know with certainty that the other one will be measured as horizontal as well. Similarly, if it's vertical. But you can't control what the outcome is. It's random, which is why you can't use it for superluminal communication, which is a common misconception.
So I think you were I just cut you off. You were explaining what the benefit of that is, but just so I understand, like, what can we do with that? It's not immediately obvious, like, what we can do if these things are entangled at a distance and I can measure one and then know what's going on with the other one. Like, what are the benefits to something like that?
So at the moment, all they've really done with it, because it's an easy protocol, is quantum key distribution, where the goal is you and I want to share secretly a random sequence of binary digits that we're going to use for an encryption protocol. So this is a common problem with classical cryptography, is that they have good encryption codes for private key cryptography, but because that private key cryptography, you need it in the dark back alleyway where you make sure there are no security cameras watching and exchange pieces of papers, to exchange a private key. So instead, we all rely on public key cryptography. The idea that the key that's used for encryption is different to the key that's used for decryption. And so you can make one of them public and everyone can send you messages, but nobody can actually read them, okay? But private key cryptography is very secure compared to public key cryptography, but you've got this pragmatic problem that you need to meet secretly. Quantum key distribution allows you to use this combination of this random measurement collapse phenomenon combined with the fact that they're perfectly correlated, such that the two distant parties that each have one half of the entanglement, they're guaranteed to get consistent results. And if there was an eavesdropper in the middle trying to intercept the random signal, you would be able to know it, because when they measured it and then did an intercept resend attack, they measure the result and then resend it, they would be resending the collapsed version, meaning that it would disrupt the consistency between the two endpoints. So if they were to then just sacrifice some of the bits and compare them, they would very quickly identify whether there'd been an interceptor or not. So this is really all that we've done with these quantum key distribution links. The next step is doing something called quantum state teleportation. If you and I have an entangled pair between us, and I have a qubit, an arbitrary qubit that I want to share with you, what I can do is interact it with one half of the entangled pair on my side, then send you just some classical information over a normal internet, and then that classical information combined with your half of the entangled state will allow you to perfectly reconstruct this qubit that I had over here, even though I didn't actually send the qubit. So that sounds like a rather contrived problem. It's actually very useful. So the context for that is in classical information, you can arbitrarily copy data. If I send you a Word file, you can make as many copies as you want. And now suppose you had an unreliable internet between you and me.
Don't jinx it.
Well, yeah, sure, but I can guarantee you there are packets being lost right now. But it's not a problem because you can just resend them, right? And that's what our current internet protocols like TCP/IP do. They send a packet of data, and if through network collisions or competition it doesn't make it through, it just tries it again, no problem. At the end of the day, it all gets through. With quantum information, it's a bit different because you can't arbitrarily copy an unknown qubit. If I give you an unknown qubit, you can prove, in theory, using a very simple proof, that there is no physical way to make multiple copies of the unknown original qubit. So what it means is that I've got a qubit that encodes useful information like the output to a computation that's a value or something, and I want to send it to you on the other side of the world, and that network is unreliable. If it's lost, it's lost. You don't get it back. You don't get to make a copy and try again. This quantum state teleportation trick lets you bypass that. What you do instead is you just attempt as many times as necessary to share entanglement between the two endpoints. When that succeeds, you use quantum state teleportation to teleport this unknown qubit, but it bypasses the actual quantum channel. You're only using classical information at that point. So it's a very, very effective in making a quantum network robust against things like noise and loss in the network. And it's a technique that is necessary because quantum information can't be duplicated.
Mm-hmm. So I know in this book, some of it is it's like a vision of the future, right? And some of it might be somewhat speculative. Some of it might be, there'd be a range of things that are, in terms of likelihood of coming to pass. Let's say some of it might be quite certain. Some of it might be more speculative. What is more speculative? I want to hear about some of the cool or maybe weirder things that could be possible with this.
Okay. So as we've discussed, if we imagine a future world where quantum computers are all over the world, the way big data centers are all over the world, well, for the reasons we've already gone over, there'd be huge value in networking them all together, because then they would collaboratively provide something, even on a time-shared basis. All the users would get something far greater than just using their resources individually. So that immediately economically incentivizes building infrastructure, a quantum internet, to connect all of the world's quantum computers into one. You can immediately see the value in it. So now let's suppose that exists and that all of the quantum computers in the world are connected by a global quantum internet. Well, it sounds very rosy that this is a huge incentive for cooperation. We want everybody to jump on board and starting into this big unified global quantum computer where everybody gets way more than what they contribute. However, it could also be used for leverage. It could, and it has huge strategic implications, because the applications of quantum computing are very much dual use technologies. They can be used for good purposes and bad purposes, like cracks versus civilian use. So it may very well be the case that the nation states that have the lion's share of this architecture, even though they would in principle benefit from a computational perspective from allowing some adversarial state to unify their computers, they might choose to reject them nonetheless on the basis that they don't want them to have the extra computational power, even if it means we have less too. So this is where it starts getting a bit game theoretic. If you imagine a highly polarized global environment where there's a computational arms race, nations would be thinking very carefully, well, if I cooperate with this other nation, yes, I'll get more computational power, but so will they. Is that worth it? Is it worth it for me to have more computational power if the other person is necessarily getting more computational power too, and they might be using it against us, like cracking our own codes, for example.
Yeah, it seems. I was just thinking while you were speaking, I was thinking there's so much utility in everyone cooperating, but then if everyone cooperates, it gets tricky because if there are those, if there is a bit of antagonism between countries, like there always has been, but there is a bit today. Do we actually want them getting access to that power, right?
You can think of it in an analogous way to global trade at the moment. I mean, it's pretty well established that if everybody is able to freely trade, that is the best case scenario in terms of economic growth, is that everybody's able to trade with everybody else. But do we actually see a world in which we have global free trade? Not even close. You have countries sanctioning one another and cutting each other off and using it as leverage to threaten to cut one another off, or waving it as a carrot. If you do this for us, we'll let you trade with us. So we already see this taking place with trade at the moment. The difference now is that the multipliers are very different. If we're trading, some conventional items, we make a little bit of extra money. If we're unifying quantum technology, the multiplier there is potentially exponential. So it changes the game theoretic consideration significantly, but the same principles exist.
I was going to. So I heard that. Firstly, why is Australia overrepresented in terms of quantum computing prowess? Like,
Yeah.
I checked. I've did some googling before this, and I have done so over the past couple of years because this is just quantum's cool, right? It's just one of those words.
Yeah.
And Australia seems to be killing it.
It's interesting. So really, you mentioned before that you studied at the University of Queensland. That was essentially the epicenter of Australian quantum computing research academically, and also very much a global center in terms of intellectual capital. We had lots of the really foremost people at the University of Queensland back in the early days, at the time when I was doing my PhD. We had this incredible overrepresentation of world-leading figures. It's not quite like that anymore. It's all dispersed around a lot. But I think really it's hard to diagnose what the reason for this was, but we have a disproportionate number of brilliant Australian thinkers and early creators in this field. Unfortunately, now as the world has started seeing the economic utility in quantum computing, and there's all this private sector investment coming into it, lots of it has fled overseas, where it's easier to get access to large amounts of venture capital and seed funding than it is here. So if we look at some of the big companies in quantum computing at the moment, one of them is PsiQuantum, based in Silicon Valley. The two founders are both Australians. One of them was a colleague of mine at the University of Queensland, but they both went over there to found their company there. Another big one is Xanadu in Canada, also founded by an Australian, by one of my PhD colleagues, in fact. So for whatever reason, once you have a certain amount of intellectual capital to begin with, they train the next generation. So we had a few generations of really big thinkers in this field, but then the ones that decided they needed to make a lot of money by making companies, they took it offshore, unfortunately.
Yeah, well, we are really bad in the OECD, or amongst more developed countries, at transforming science into going from science to industry, like innovation, right? Capitalizing on those things. But I did see that an Australian company developed. I don't know how legitimate this is, but developed a quantum computer or a quantum chip that can work at room temperature. Is that right?
Oh, are you thinking of this Quantum Brilliance company where they're using
quantum? Quantum Brilliance.
That's right. So they're using Diamond, the I know I don't understand the full details of the architecture, so I'll try to avoid making too big statements, but they ultimately rely on defects in a crystal structure, where you can also have levels, energy levels associated with things like defects or implanted atoms in diamond or whatever kind of defect. Yeah, so those ones are an example of one that can operate at room temperature, but so are the optics, because light isn't affected by temperature. The ones that are really affected by temperature are obviously things like the superconducting rings, because superconducting necessarily is very low temperature. Also, if you've got, thinking back to our earlier discussion about energy levels in an electron, well, what is actually temperature in a bunch of atoms? It's vibrations, and it bumps up the energy levels of the electrons into higher energy levels. So if you've got information stored very carefully between two particular energy levels, temperature starts fluctuating those things around and bumping them around, and you lose your information. It's certainly, all of the optical ones would be room temperature as well.
Yeah, okay. Yeah, it just always struck me as, just going back to, it struck me as a bit odd that we're a relatively small country and we seem to be overrepresented there.
We are. Yeah.
I wanted to change pace a little bit and I guess talk about encryption and blockchains and what quantum computers can actually mean for privacy. So as it stands right now, could a sufficiently advanced quantum computer break or crack a lot of the encryption that we use today?
Right. So this is where it's a bit nuanced, and it's also where the media quite often gets it wrong, because cryptography is also a highly mathematical and quite specialized field. And cryptography is really a branch of mathematics. So we've got two main types of encryption that we use, and we've mentioned them before: private key cryptography and public key cryptography. Private key cryptography is when we meet in secret to share a key, and the same key is used for encrypting and decrypting messages. So you and I would have the same key. Public key cryptography is also called asymmetric key cryptography, because the key that you use for encryption is different to the key that you use for encryption. So if you make public the key that you can use for encryption, and keep private the key that is used for decryption, then so long as it isn't possible to infer the private key from the public key, then anyone can securely send me a message and I don't have to worry about interceptors. Obviously, that's much more practical, right? Because on the internet, that's what we need to do. We don't have the ability to meet everybody in the world in advance to share a secret key. So we really, really need public key cryptography. Now, to the best of our understanding, quantum computers do not compromise our existing private key cryptographic techniques. So they're fine. They do compromise our primary existing public key cryptography techniques. We have two that are used predominantly, RSA and elliptic curve cryptography, ECC. So I can explain briefly how RSA sort of works. Here is that you take two large integer numbers and they represent your private key. And there's a mathematical procedure that you can use for decrypting the message using the private key, those two separate numbers. If you multiply those numbers together, you get another single large integer, and that's the public key. And there's another mathematical procedure that you can use to use that public key to encrypt a message. And the reason it's secure is because we don't have an efficient classical algorithm that allows you to factorize long integer numbers. So
to basically figure out how many different ways that number could be, how many different ways you can multiply two numbers to get to that number?
No, so actually I should have mentioned, we start with two prime numbers. And so when we multiply them together, there's one unique way to factorize them back out into its two prime constituents. So going one way is easy. We all know how to multiply. We can do that by hand. Going the other way is, on classical computers, one of these things that is extremely inefficient. And so if I give you, a 4,000-digit integer, which is the product of two prime numbers, and say, figure out what the prime numbers were, your classical computer can't do that. But your quantum computer can do that using this algorithm invented by Peter Shaw called Shaw's algorithm, and it can do that efficiently. So what that means is that in principle, if someone had a quantum computer, then if you and I had a secure video link, the way we do now, in principle, they could come in and intercept that. Now, when it comes to things like the blockchain, we use another cryptographic. It's not just encryption that we're using. In fact, we don't use encryption in the blockchain at all. We use digital signatures. Digital signatures work the same way as RSA public key cryptography, except you're reversing the roles of the keys. So that now I make a key public, which anybody can use to decrypt the message. And I keep the key private that can be used to encrypt a message. Okay, so what that means is that I can encrypt something and anybody else can be sure that it was me that encrypted it, because I'm the only one that had that private key. So we're just completely reversing the roles. That's your signatures. So I can put a key on my website that you know belongs to me. And if I send you an email, I can sign it using that key. Anyone in the world can look at my public key on the website and say, it was definitely Peter that signed that, and nobody can forge it. Okay, but it's the same cryptographic algorithm. That's used in the blockchain and also for obviously signing documents. So in the blockchain, what we do is whenever someone makes a transaction on the blockchain, it's signed off on by what's called a consensus algorithm, whereby a whole bunch of other randomly selected individuals involved in the network use a digital signature to say, yes, I attest that this is a legitimate transaction. So they basically witness to say, yes, we collectively confirm that we are witnesses to this transaction, and at that point it gets committed to the blockchain. So if someone could fraudulently fake digital signatures using, for example, Shaw's algorithm, they could fraudulently sign off on other people's behalf and make false transactions on the network. So in principle, they could take all the Bitcoin or invalidate the smart contracts or manipulate the smart contracts, that kind of thing. So that's where the interplay between quantum computing and the blockchain comes in. But it gets a little bit more nuanced than even that, because it's not the end of the world, because people are inventing new types of cryptographic codes that even quantum computers cannot crack. And this is the field called post-quantum cryptography. It's a very
post-quantum
cryptography.
Post-quantum. We're going beyond quantum.
That's right.
New age people, look out.
Yeah. And it's not a completely solved problem yet, and at least in the sense that it's not standardized the way conventional cryptography is.
Okay, so should we be concerned about, should those in crypto be concerned about the existing technologies and their viability for the next 10 or 20 years, perhaps?
Yeah, the answer is yes, because things like, almost all of the existing blockchain technologies that are use our existing public key crypto systems like RSA or elliptic curve cryptography, which means that when someone comes along with quantum computing, they could invalidate transactions or undermine the network.
Yeah.
That does have long-term implications, even though we don't have quantum computers now. So for now, your Bitcoins are safe. But if you now start thinking as a technologist, but as an economist, how does an economist value things? They value things by looking at what their future price is and discounting it according to inflation or interest rates, right? This is how people value bonds, for example. They say, well, this is how much it's going to pay in 20 years at maturation, and then I discount that value according to the interest rate to figure out what its present day value is. So if you have an asset, you're pricing it according to a forward pricing model, but you know that in whatever period of time it's going to be invalid, that also undermines the value of it now. So this is where it gets more complicated. So people should be concerned. I don't think that people really are, because they're probably hoping that there's going to be a hard fork of things like the Bitcoin network into using post-quantum cryptography or something like that.
So have you considered pivoting your career and building Quantum Coin?
Well, actually, there are plenty of people already doing this, building quantum-resistant blockchains. There's one called the quantum-resistant ledger with a well-chosen name. There are various others that are looking at using post-quantum cryptographic techniques in their blockchain networks. So people are already starting to transition to this for the obvious reason that when we're talking about things like smart contracts that need to be valid in the future, well, you need to ensure the cryptographic integrity of it in the future as well.
Yeah, and it could become a social security risk if countries start adopting Bitcoin more and more. I mean, I know El Salvador is accepting it as legal tender, and let's say if some countries, yeah, you get what I'm saying.
Yeah, that's right. And you know, all of the different currencies are sort of designed differently. But there's this one common idea, this idea of doing what's called a hard fork, whereby you effectively swap all of the registered transactions from one network over onto an alternate blockchain. So you could do a hard fork to transition the current Bitcoin network to a post-quantum one at some point in the future. That's one way around this.
Yeah. Okay, well that makes me feel a bit better. I saw that, I think it was maybe last year or 2 years ago, you wrote a paper with a guy that I had on earlier on this year or maybe last year, Professor Jason Potts, on the topic of quantum cryptoeconomics. And when I saw that paper, I was like, God, what an amazing title. I mean, that was in the title, but just talk about buzzwords. And I don't mean that
it's got everything
at all. It's got everything.
All it's missing is nanotechnology.
Exactly. And sprinkle a bit of artificial intelligence in there, you know?
That's right.
So I think one of the things I read in that was that, and please correct me if I'm wrong, but quantum computing technology could help us mine faster. And that could actually be a part of the problem, right? That actually fits into the problems here.
So the mining question, this is where now it turns to a nuance of the way cryptocurrency mining works. There are different ways in which different cryptocurrencies implement mining. One specific one, which is used in the original Bitcoin cryptocurrency, where it's called proof of work mining. And the idea there is that you need to solve this particular mathematical problem called inverse hashing, which is something that by definition, and it's chosen for this reason, takes classical computers a long time to do. So I can explain how it works. A hash function is what's called a one-way function. You input some sequence of bits and it spits out a short digest, a checksum. This is used in all sorts of things for making checksums in various protocols. But the point is, it's a one-way process. It's very hard to go in the other direction unless you exhaustively try different input combinations. So that's what you have to do. So the way
just so I understand, and those inputs, if I put in these bits and I get that hash, if I put in the same bits into the same function, I will get the same hash. It's consistent every time, right?
Oh, it's deterministic.
Like same inputs.
That's right. Yeah, that's right. It's consistent. It's deterministic. But it has a highly cooperative behavior. It's not actually random, but it kind of behaves that way, in the sense that if you make very small changes to the inputs, you completely scramble up what the output of the hash is, and the defining characteristics of hash functions. So the way Bitcoin mining works is you've got some input string, which you're hoping is going to be a Bitcoin. It's defined as being a legitimate Bitcoin if, when you hash it, the output bit string has a certain number of leading zeros, okay? And the leading zeros is what determines the likelihood of using randomized processes of finding an input string that satisfies the criteria. So you have to go through it just by trial and error. You randomly generate bit strings, put them through the hash function, say, does it satisfy the output criteria? If no, try again. And it's called proof of work because it takes a lot of work to do this. You have to go through this many, many times to get the answer right. And this is where one of the big criticisms is at the moment. You might have heard how currently the Bitcoin miners are consuming an energy equivalent to a medium-sized nation state's energy consumption. That's because they're just wasting all of these CPU cycles, taking random data, putting it through this function, saying, does it match the output? It's completely wasted computational power other than just trying to find random bit strings that satisfy property. But that's how Bitcoins work. Now, the way this hash function inversion procedure works is there's a quantum algorithm called Grover's algorithm that lets you slightly improve the efficiency of that process. It gives you, remember our discussion about scaling, it gives you a quadratic improvement. So roughly speaking, if it takes n attempts to find a matching output using a classical computer, it'll only take square root of n attempts to do it on the quantum computer. So you get a quadratic improvement in the rate at which you're mining coins using the quantum technique. However, people are moving away from proof of work mining protocols to proof of stake protocols, and actually consensus protocols, and the way to design well-designed cryptocurrencies that overcome these problems of massive energy wastage and inefficiency. It's a massive area of research, which is exactly the sort of thing that people like Jason Potts are looking at. So Bitcoin is kind of giving cryptocurrencies a bad rap because it was the first one that was designed. It was incredibly inefficient, resulting in huge energy wastage, but it doesn't need to be that way.
So I've heard that those sorts of that proof of work strengthens the security of the network. I don't know enough about this to be able to really comment, but like that's what I've heard. But what are your thoughts there?
Yeah, so proof of the connection between mining and the consensus algorithm. Remember how I was saying that the bit when you make a transaction with Bitcoins or a cryptocurrency, there's a consensus algorithm that everybody else, or at least some selection of other people, have to sign off on it to say, yes, this is legitimate. So the connection here is that when you successfully mine a coin, that coin becomes validated when you sign off on someone else's transaction. Okay, so mining a coin and it becoming legitimate tender is your reward for signing off on other people's transactions. And this is how that whole economic framework is self-incentivized and doesn't need any external forces to encourage people to come in and be kind enough to sign off on other people's transactions. It's incentivized because the reward is validating the coin that you've just mined. So now the problem is that there's a finite number of coins and it's getting harder and harder to mine them. And so the energy usage is going up to maintain the network.
Just need a bit of nuclear. Need some nuclear energy. Clean this stuff up a bit.
Well, it's much better just to switch to a more efficient type of protocol.
Yeah. I don't know much about the specifics of, like, the technicalities of Bitcoin's blockchain versus others, but the thing is, it's the first generation of its technology, right?
Yeah,
and
that's right.
Chances are it didn't get it right straight away. Like, it didn't get it all right. It's not the best.
Exactly.
Chances are there's going to be other ones that are better.
Exactly, and there are much better ways.
Yeah. So I'd be interested to see what happens with Bitcoin over the years because of that. Because it's got a lot of belief. It's got a lot of religious support to a certain degree.
Yeah, I mean, it has a lot. I think because it was the first one and it's the best known. It's not the best. Transactions are slow. Has a low volume of transaction rate globally. It's hard to know what the future of individual cryptocurrencies is going to be. That's a whole thing that I'm not going to get into because the whole thing is so dry psychology that it's hard to make factual statements. But certainly in the long term, we're not going to be using protocols like that. We'll be using next generation ones, which, as you said, get things right.
Yeah. So I think what does being a crypto anarchist mean to you?
Right. So for me, I sort of coined that term because it combines the term of political sort of libertarian anarchism with cryptography. That is, I'm a huge advocate that people have a right to use cryptography. It should not be infringed upon. I completely oppose any kind of government measure to input backdoors into cryptographic products or into physical devices, and completely oppose any legislative measures to prevent people from using cryptography. Because yes, it's true, cryptography can be used by terrorists and pedophiles and all the bad people in the world. Of course it can. Every technology can be. There's no denying it. But on the whole, securities are safer. So you need to look at the cost-benefit analysis. Yes, it has bad uses, but that gets far more attention than it deserves. And the reason is because politicians don't want us to have cryptography because they'd like to work against us and have us under their power. So they use highly emotional terms like terrorism and child protection, but they don't actually care about these things. They just want to get in and read your messages for other reasons altogether.
Yeah. So when you say crypto, it's actually crypto as in cryptography, not as in crypto blockchain Web3 type stuff.
I support.
You see them as connected.
They are connected, yeah, and so that extends to cryptocurrencies as well. I support completely allowing the advancement of cryptocurrencies and allowing people to use them. I don't think the law should be infringing upon them in any way. So again, politicians, they say, oh, we can't let people use cryptocurrencies because they'll use them to trade drugs and arms and money laundering. Well, yes.
Or avoid paying tax. I think that's so. What I think, I am not confident in. I think governments are probably going to crack down hard over the next decade on cryptocurrencies for various reasons. I think but I think that'll be good for crypto in the short run, because I think the world's going to be weird for the next 10 years, right?
Yeah.
I don't think we're out of the woods yet with COVID. We're far from out of it. I think a lot of the impacts still haven't been felt. And I think we might see some instability in some countries. The currencies go a little bit crazy. People try to put their currencies into something safe, right? Because their savings are currently, they're losing all their value. So what are people going to do? They'll probably try to buy US dollars or buy crypto. Probably crypto, because it's a lot easier to buy crypto than gold. Or if you want to go to your bank to buy US dollars, the government can just say no. So I could see that happening in some countries soon. And then, I can just see, so there's that, but I can also just see countries cracking down on crypto and trying to force them to use their own government-backed coin. And
Sure.
I don't
this
like
is
that
exactly what China is doing.
It's freedom, right? Yeah.
So coming back to what you were saying before about people using cryptos because other things. There was an interesting case study of this in Venezuela just only a few years ago, when there was hyperinflation taking place because the government was printing heaps of money and there was huge political instability. You can look on because Bitcoin, you can see the transaction flow. Looking at the IP addresses and things, you can actually see on a region what the regional trading volume of transactions is. So in Venezuela, you could see this very, very pronounced visual, looking at the graphs, visual connection. As there was political instability, the local trading volume in Bitcoin started skyrocketing because people were switching to it as an alternate form of currency because the government's actions were hyperinflating the fiat currency in that country. So as people lost confidence in the nation-backed currency, you saw people switching to using cryptocurrencies. Now, in the old days, people would have, bartered directly. Why wouldn't you let them use cryptocurrencies? Why restrict people to using barter? And why would you mandate people to using a currency that's going to collapse? And it's not as though the notion of governments not being trustworthy with currencies is restricted to, a small number of countries. There's a long history of countries doing this.
Yeah. I lost what I was about to say, but my belief or confidence, and I think this is true for a lot of people in governments, is a lot lower than I guess it used to be. And I think it's going to continue to go down. And so I don't really want them to have that degree of control, particularly in Australia. Like, I've been quite concerned with the loss of our freedoms over the past decade or so, particularly digital freedoms, which you don't really hear too much about in the media because it's not as obvious, right? Like, if there's a law change.
And some of it is really, really nefarious and underreported, I think, by the journalists.
Yeah.
Like
the surveillance, the one a couple of weeks ago.
Law, right? So for example, the fact that the federal police have the legal right not just to go in and read stuff off your computer, but they're allowed to edit it and put stuff on there. That is a legislation allowing the police to impersonate people, frame people, set people up, put false evidence on people's devices. Like, how in a free democracy does legislation like that just come under the radar with nobody saying anything about it? Well, because there was
no one's really like, there's not too many people talking about it, and this happened maybe a month or two ago, and there's radio silence among. Like, I'm not hearing much about it, and this can be like you just can't trust the government. Like, this is like one of the problems. You just need to give. Unfortunately, especially in our world, I wish that we could trust the governments to be benevolent, right?
That's right.
I wish that we could trust, but I do not feel that way now. So I do not wish. And we're seeing in Australia at the moment the abuse of power, at least in New South Wales, with Friendly Geordies, the online comedian who highlights corruption, and he's a bit of a larrikin. But I think the deputy premier has been got some special task force. I can't remember what they're called. The something persons unit.
That's right. That's right. Some special police unit to go after him.
Yeah.
I mean, it's just
And
blatant abuse of power.
yeah, that much is obvious.
What it demonstrates is that being a democracy in the loose sense that we get to vote for our leaders does not mean that we're a democracy in the strong sense of having transparent government that acts in the interests of the people. So let's call that weak democracy versus strong democracy. Weak democracy doesn't mean squat. It really doesn't. The ability to just vote for your leaders does not guarantee anything about the quality of your government. What guarantees the quality of your government is the ability to hold them accountable and not to allow them to accumulate too much power. And this has always been the argument of the libertarian and anarchist movement. And I'm not an anarchist in the normal political sense, but this is where that term crypto-anarchy comes from. Well, yes, right to speak to you in private. The police don't have a right to just arbitrarily come in and then plant data on my computer. So this is a perfect example of why it's a fundamental right in the digital era to be allowed to use cryptographic technology. And I shouldn't be prohibited from using it, because the only reason governments want to prohibit you from using it is because they know that it undermines their ability to abuse power.
Yeah, it makes me somewhat concerned, like, about so the more information someone has on you, like the government, the more they can help you at times and the more they can screw you over, right? So I'm thinking about, like, if I go to hospital for whatever reason, I want the government at that point in time to have as much to know as much about my health data, even have my genome on file or whatever, so that they can deliver the best level of care. But at the same time, I don't want them to have access to all of that information all the time, because they may be able to influence me in some way, or influence other people. And we're at this really weird period where there's trade-offs, and I don't know where.
There's a huge amount to be gained and a huge amount to be lost if it's used the wrong way.
Yeah.
I mean, here's where it comes down to, one government department using information for a specific purpose can be hugely beneficial. But if the ethical separations are not properly observed, it can be extremely detrimental. So a good example that came up recently was police using COVID check-in data to try and track down criminal suspects. Now, that data is guaranteed, by the politicians. It's there for health tracking only. That's our social contract with you. We're using it for contact tracing for health purposes only. What do you know? It turns out that the police were illegally intercepting that data to use it to track and identify people for purposes of investigation. So this is another weakness in democracy, is that simple ethical considerations just aren't observed anymore, and it's very hard to enforce them.
Especially with this weird place with the media. I mean, I don't engage much with the mainstream media at all, mainly just because I get most of my information through my device and I've got my own sources. I'm not going to, the conspiracy subreddits and like getting everything from there, but I just keep my tabs on the world through other ways, not through watching a current affair or,
Sure.
I will put the ABC on sometimes, right? But I feel that the majority of, at least here in Australia, but I would say this is the same for most of the other countries, at least in the West, a substantial portion of the population still gets their information from television, from the newspaper. And here in Australia, they are controlled and they have by, Murdoch.
Well, even more than that, it's not just what the news sources are, it's what leads them to those news sources. And to a lot of people, it's what's recommended by their social media feed. So it is very, very common these days that even though the news sources might be the same and have the problems you mentioned, domination by Murdoch, that kind of thing. The point is the individual articles that they're reading are presented to people in an algorithmic way, which is amplifying arousal, so to speak.
Yeah.
Those algorithms capitalize, they cash out on clicks. So they're basically taking all of the media out there, rhythmically amplifying the stuff that gives people that wow factor. Well, it's very easy to see.
The rage factor.
Yeah, it's very easy to see that the obvious evolutionary outcome here is political polarization and extremism. And what have we seen in the United States? Well, there's the answer to it.
Yeah, yeah. And I think what happens there kind of happens here a little bit later. You know, I think it's not, maybe it's more pronounced and I guess caricatured in a way. It's like, it's Americanized, right? But I still see that trickling down to Australia and elsewhere.
No, I agree. And like I think that there's a lot to be said for enabling more independent journalism. There would be enormous value to society in seeing greater media diversity coming from different types of sources, the way you just described you do for yourself.
You know, I had this idea ages ago. I would love it if the government gave everyone a token, you could say, that's paid for by the government solely to support musicians or artists or independent journalists, and you can choose how much you give per year, and the government then pays them the amount.
So it's almost like direct democracy for allocation of funds in a sense.
Yeah, well, it's like how much money gets given to the arts, the Department of the Arts and whatever. I don't know what they're called, but probably a lot. Take 5% of that and then just give it to the people and let them vote. With that, just let them give it to the artists and the causes that they care the most about. Because it's more efficient.
That's right. And what you just described is a very simple way to avoid situations like the Premier ended up having to resign because of an ICAC investigation, is if instead of those decisions being made at that level, it was done using something like what you said. The government decides to allocate X million dollars for arts funding. Well, here you go, everybody, you can vote on it, and here's how it'll be proportionately distributed. This is all pretty simple technology to implement. It's not hard.
And we have the technology, right? It's not like this is...
It's not new either.
No, and governments they're good at some things, and one of the things that they are good at is getting money to people, right? Like that's one of the only things, like they've got the infrastructure to pay millions of people something. So, I mean, the payment, getting it there is one thing. I mean, the user interfaces for all these things leaves me wanting. Our MyGov, the identity system sort of stuff that we've got here is a bit frustrating, but
sure.
Yeah.
And then there are also concerns there because there have been a number of data leaks coming from major government departments over the years, which raises serious concerns about whether it should be in a centralized hands of government like that, or on some kind of encrypted public ledger, like a blockchain for your health records, where you get to control who has access to what, for example, rather than the government department doing it. That kind of thing is under active research as well, and is a huge pro-democratic kind of initiative.
Yeah, what concerns me about that, and I don't know too much about it, and I haven't thought too deeply about it, but let's just take DNA data, for instance, right? My DNA is static. It's immutable, really, across, like, there might be epigenetic changes, but like, my DNA is my DNA.
Yeah.
Let's say that I want to give it to some company to run an analysis on me, tell me what sort of vitamins I might be more likely to be deficient in, or I can't, like, just to tell me what problems I may encounter in my life due to my genetic makeup, right? Or other things. Like, there's a variety of uses for DNA. I would like to give that company my DNA, but I would not like them to have it across time. Something like that. Once I give it to them, they could just copy it, and then they've got access to my DNA for the rest of my life. And then a insurance company could buy that and say, "Oh, we're not giving you health insurance because..." Yeah. So I've yet to. I don't know how we can empower. I'm sure there'd be techniques where you could.
Oh, sure. I mean,
destroy the data
this is an
afterwards.
Example of where cryptographist techniques can be used to anonymize things, for example. So certainly you could facilitate the transfer of data in a way that it gets from one person to another recipient back to the original person, but in a way that it isn't possible for the party on the other side to know the identity of the individual. Those sorts of things are enabled using cryptographic
zero
primitives.
knowledge proofs.
Is that kind of like zero knowledge proof? That kind of flavor, right.
Yeah. And I just jump in. There's like something like that would be so good if we had a global bank of DNA data that we could run analysis of. Like there's a really strong utilitarian argument for that, right? Like it'd be incredible as long as it just doesn't screw people like the individuals over. And we can't trade. That trade-off isn't worth it.
If you had all that data anonymized and open access to researchers, I think this would probably be a wet dream for genetics researchers to be able to access to that kind of stuff and put it through data processing to learn all sorts of amazing things. But the privacy issues are a big one.
From what I've heard, we can't quite anonymize data effectively yet. Supposedly it's pretty easy to
anonymizing data. Yeah, anonymizing data isn't so much the issue. The problem is that when it comes to something that starts with a physical blood sample, there's a physical recipient, and it has to get back to the same physical recipient. It's not a purely digital interaction. If this was purely digital and you just wanted to anonymously transfer money, you can do that, right? There are anonymized blockchain or cryptocurrencies that can do this. That's no problem. The problem is when it converts to something from cryptographic or digital to something physical. At that, is the weakness in the security.
Yeah. Well, Peter, I think we'll wrap up shortly. I guess just a few wrap-up questions. What are you currently really excited about?
Yeah, it's hard to say. There are a lot of interesting things happening in the world, but I do find the whole era of crypto economics, not necessarily quantum crypto economics, but like just crypto economics, decentralized services, which are a sort of extension of some of those principles, moving away from a digital world where everything is monopolized in the hands of large players that ultimately are there to data mine you and make money by exploiting your confidential information. The next generation, where we start moving towards decentralized apps, away from centralized cloud service to things that are truly decentralized, that I think is probably the most exciting next stage of technological development, especially coming from a sort of pro-democratic, freedom-loving perspective.
Yeah. And there's a lot of energy in the world right now around these sorts of things.
Oh, yeah.
I mean, at least on Twitter.
And a lot of political opposition to it, too.
Yeah. Well, I believe in the end, freedom always wins. Not just that. That's not like a wishy-washy, I have faith, but I think it's kind of technically it is the case in most instances, because if you constrain freedom, you constrain potential pathways, and by maximizing diversity, you end up coming to some solution.
Yeah, so I'd maybe paraphrase that as people have an innate desire for freedom, and if you stifle it, you also stifle their incentive to innovate and to create and to produce, which is why creating freer societies is inherently better than highly controlled ones.
And it's a positive sum game. If someone does something really well, as we've seen over the course of the past few centuries with economic development, it's not isolated, right? Like something gets developed in one country, that information travels across the world, processes get better everywhere, everyone gets happier.
Right. Yeah, exactly.
Yeah. Well, Peter, where can people? I mean, obviously, check out the Quantum Internet. People listening, that book's just been released, and so where can people find out? Yep.
So
give us another
published by. This is is published by Cambridge University. You can get it from the Cambridge University Press website, or also on Amazon and probably various other online suppliers as well. If you live in Sydney,
I think I've seen...
I'll autograph it for you.
Yeah. We'll have to catch up in Sydney sometime. I mean, we are free, so we could have done this interview in person, but this is a lot easier. Like during the interview set up in person is a bit much. But yeah, it'd be good to catch up in person anyway.
Let's do that.
And I've loved the pictures of all the world leaders holding the quantum internet.
Well, I wonder which countries I'm banned from now.
Yeah, maybe Russia.
Yeah.
And if people want to keep up to date with your work, I'll list your Twitter profile and your website and all that in the show notes. But are there places where you're more active?
Oh no, those are the main places to look. They all link to one another, so yeah.
Yeah, awesome. Well, Peter, thank you very much for taking the time. It's been a lot of fun.
Thank you very much, Sam. Appreciate that. Really enjoyed it.